you very much and welcome everyone today. It's always lovely to be up first. My name's Andrew Corney. I'm Product Director at Sefaira and today we're going to talk to you a bit about what ASHRAE does and go through some specific case studies that we've been working on, or some specific use cases we've been working on recently with the software. My background, I was a building services consultant for 13 years, an ASHRAE member, an SMT member and a licensed engineer, but I've since in the last 3 years been working at Sefaira, trying to help make software that's relevant and exciting for people in our industry. There are about between 400 and 500 firms around the world that are customers of Sefaira, and about 200 or so educational institutions using it for learning as well. And one of the things that attracts people to Sefaira, the sorts of people that like Sefaira, are architects. About half of our customers are architects, a bit more than half of our customers. People who are new to building simulation, who find the learning curve a bit too steep to dive into some of the more advanced software. We provide a really great way to get started into building simulation. And also professionals who are used to using simulation and other tools, but who need something that's a bit more productive, has a higher efficiency rate at the early stages of design. So Sefaira is essentially a good design tool to do very good analysis at the early stage of design very easily and quickly. So we'll talk a little bit, I think it's always worth talking a bit about what the problem we're trying to solve as a software product, especially since we're not trying to solve a compliance problem, and a lot of software out there is designed to help people be able to achieve compliance. Generally speaking, what we're trying to do is help people design better buildings during the early stages of design. So we'll just quickly talk about that, and then I'll give you some examples, and particularly the first two will dive into a fair bit of detail about designing naturally ventilated buildings, and not just talk about the software, but about techniques to design naturally ventilated buildings fairly quickly during the early stages of design. Hopefully I'll be over before the 45 minutes is up, and there'll be an opportunity to ask questions at the end. So what's the problem we want to solve? Essentially, design teams want to consider building performance as early in the design as possible. Hands up if you think that considering building performance early in the design process is important. Yay! At least half of you. That's great. So why do people think this? Well, at the beginning of the design process, obviously, is when the key decisions are made. If you get some good decisions right early on in the design process, it can help the design team from having to do rework and extra work later on in the design process. And importantly, if you're in a business development role or in a leadership role in a business, that's when your client is watching what you're doing on the project. Most of the time, once we get to Reba Stage 3, most of the senior people attend meetings less and less, and the work is carried out by perhaps not the people who are making decisions about employing people on the next project, but at the very beginning of the project, at the kick-off meeting, everyone's there and they want to know what your greatest and latest is. What are some typical early stage design tasks that, that we know that people are doing during projects? Well, very early on, and this is a bit extreme, but early on people might be comparing building forms. Is this form better than that form? Assessing some preliminary passive design strategies like shading on the building, how effective is different shading strategies, or how effective is natural ventilation going to be. Get preliminary guidance on daylight. Am I bringing enough daylight into the building with the form that I have? Testing some preliminary energy and carbon reduction strategies for a project. Choosing the HVAC system. A lot of the time during Reba Stage 2 we're trying to make a decision about the HVAC system we're going to proceed with, and a lot of people want to know more and more, want choice, or at least the impression that they're going to get to choose what system they're using. And you know, more and more now, checking the design is comfortable and healthy. Hands up if any of you do any of these sorts of tasks or think about these sorts of things early in the design process. Yay! A few, there's a few, but still quite a few of them, that's great. Now, the problem with doing these tasks early on in Reba Stage 2 or during the early stages of design is that to do these tasks effectively or to do these tasks well, there are two key requirements. Speed and accuracy. Okay, and because I'm Australian, I like to represent things in boomerang shapes. And I think that the solution space that exists today for a lot of people in the speed and accuracy world for early stage analysis looks a bit like a boomerang. If you think about the y-axis, that's how fast it takes to get your tasks done. So at the top of the screen, it's very fast. At the bottom, it's slow and expensive. And then if you think from left to right, the left side is total guesswork, and the right side would be extremely precise. Now, we surveyed lots and lots of people. I talk to engineers engineers and architects every week who are customers or prospects or just people in the industry to try and find out what people are doing. And about 30% of engineers are just using rules of thumb during stage 2 to design air conditioning systems and select air conditioning systems, right? So rules of thumb very much fit in the fast and cheap but not particularly accurate end of the spectrum. And this is what a lot of people are doing today during REBA stage 2. Sometimes that means the results are made up, but hopefully that means there is a little bit of accuracy applied to the information. Then what people do is sometimes they're not very comfortable just using rules of thumb and they start to make spreadsheets. And what tends to happen with spreadsheets is that they take a lot more time but don't always give you a whole lot more accuracy. One of the classic things with a spreadsheet is it's very, very difficult to estimate the impact that a shading device is going to have on the load of a building using a spreadsheet. Okay? It's not going to help you that much more than using a rule of thumb. Ultimately, if you want to consider two different facade designs with two different shading systems, you'll need to build a thermal model to assess that properly. So a lot of people end up grabbing a hold of the compliance software that they use and trying to use that software to do early stage analysis. And while the software, and you're going to see lots of great software today, while a lot of software is fantastic, very precise, very good software generally, it doesn't tend to be fast enough to use or easy enough to use during the early stages of design when a lot of ideas are flying around the room and a lot of change is happening for someone to be able to use it quickly and effectively on a project. And often what happens is if the analysis work doesn't get done in time, or if the people who are doing the analysis can't agree with the person who's the principal on the project, then the results get made up because there's no time left. So what we're trying to do is we're trying to be fast and accurate for REBA Stage 2. Sefaira is designed to help you do fast and accurate analysis during the early stages of design. Why is Sefaira fast? First of all, we spend a lot of work and time making our software easy to learn. So we try to create a very straightforward interface focused on the tasks that are specifically needed to be done at early stage design, and we try to make it easy to learn even if you're not particularly experienced in using analysis software. When you create a project, we put as many assumptions as you can. We put all the assumptions that you need to get a working model straight away. So if you only have half an hour, you can still get a working energy model or a working analysis model out of the software. And at the end of the workflow, it provides really nice graphics that fit straight into slideshows. The other thing that's nice about Sefaira that's fast is that the geometry comes straight out of Revit or SketchUp. Now, I know probably a lot of you in the room might groan and say, oh, I've never seen geometry work coming out of Revit or SketchUp into an analysis tool. We do believe that our processes are very good. We're part of SketchUp. But we also use our own proprietary process to create analysis models, so we're not using any of the standard processing formats. And essentially, let's see if this is going to work. Essentially, to give you an example, in Revit, when you have Sefaira... okay, maybe I can't... I'm not quite sure if I can... okay. I'm going to explain how it works and then we'll worry about it later. So essentially the way Sefaira works in Revit is that we have a generate views function in the software. It hides everything from the view. It creates a new view for you of the Revit model, which just includes the components that an energy model would be interested in. Sefaira looks for all of the elements tagged as floors and windows in a Revit model which are generally done fairly well by people building Revit models, and then extrudes the floors, pastes back on the windows, and that's how we create an energy model. So it's a very different process to a lot of the other 3D interpretation tools. These are both models in Revit and SketchUp that work perfectly well in Sefaira with lots of zones straight out of the software. The one on the right is a Revit demonstration model that you can download from their website. Why is Sefaira accurate? Well, we run in the cloud, we run on Energy Plus. For those of you who don't know what Energy Plus is, it's an open source building physics engine funded by the US Department of Energy. It's had over $74 million worth of US government funding to date. You can decide how valuable that's been, how good that's been, but they're still investing $2 million that were invested this year. It's ASHRAE 140 certified, Best Test certified, used extensively in research, and also by Design Builder, which is one of the other software tools you'll hear about today, and many other building physics software tools. So that's a bit about Sefaira, and we think that hopefully what you'll see today is that we could be fast and accurate at doing some early stage analysis for you as well. What I'd like to do now is talk about free area and specifically talk about natural ventilation, because we've been, especially in the UK, we know a lot of people do natural ventilation design, and so we've been working a lot lately at trying to make a really nice workflow for people who have to design naturally ventilated buildings. How many of you design naturally ventilated buildings or do naturally ventilated stuff in the audience? Okay, so a reasonable amount. How many of you would like to know more about it? Yeah, okay, so it's worth going through this then. Cool, thanks for putting up your hand. Mechanical HVAC Design 101. HVAC design, if you're a mechanical engineer, is relatively straightforward using an energy model or a simulation model. You get a 3D model, whether you draw it or however you do it, you set a whole bunch of properties, you click simulate. That process might take a little while, but let's just assume that you can get through that process. You click simulate, and then you get your HVAC sizing, right? So it's pretty straightforward. You tell the computer what your building's going to have, and then at the end of the simulation, you get all the sizes that you need and all the information you need to size the HVAC system. Job done, right? It's not always that easy, but that's kind of the idea. Natural ventilation design isn't really quite so straightforward, because you get the 3D model and a set of properties, but then you can't just sort of go, okay, simulate that, and then I've got the design requirements for a system that I need. What I do is I simulate that, I get the comfort performance for the building under those conditions, and then I compare the comfort performance to design criteria, and if the comfort performance doesn't meet what I need to achieve, then I fail. I have to go back and make changes to the design and reiterate and go through an iteration process first until such point as I reach a design that achieves the comfort performance I'm after. Okay? Because we can't just make a bigger natural ventilation system, well, we can, but we can't really, that's part of the input, the architectural input that's going in. So we have to do a more iterative cycle before we can get to a place where we have the envelope requirements for natural ventilation. Now, why is this a problem? Because it means that you need to do a lot more simulation to design a naturally ventilated building than you probably do to do a mechanically ventilated building. So, how many of you know what free area is or have heard of free area? A couple of people, not that many. So free area is a really interesting rule of thumb exercise for natural ventilation, and we wanted to embrace it and use it in our product as a great way to get started, and I'm going to explain why. For those of you who don't know, free area is essentially just a way to express the relationship between the window opening area, modified as much as you like for how open it really is, versus the area of the space that it's trying to naturally ventilate. Okay? And it can be measured in an area value like meters squared if you're talking about this window has this much free area, or it can be expressed as a ratio in terms of this room has 2% free area or 3% free area. So there's different ways of expressing it. For example, the same window might have different free area outcomes depending on how it's designed. So a 1 by 1 metre area with a huge big top hung window that can open all the way out might have quite a high free area because the free area obstruction of the window is fairly small. But if you said that it had a window stopper that was 10 centimetres, that prevented it from being fully opened, and then if you had an insect screen that added on top of it, then those things would affect the free area of the window. And then if you had a 10 square metre room, that would affect the free area ratio and the free area provided to that room. Now, a lot of standards and benchmarks actually use free area. Birmingham uses free area as a prescriptive compliance pathway for ventilation. So if you achieve a 5% free area ratio in an naturally ventilated building, then you're allowed to say that, yep, I'm good, I complied with the natural ventilation requirements. Australian standard and the Californian Title 24 natural ventilation standard also use free area ratio as an acceptable prescriptive pathway for ventilation. Why is that? Because there's essentially a fairly well-established relationship, and the curve depends on the climate, but there's a fairly well-established relationship between free area and comfort and ventilation, okay? So when you get to a point where you have 5% free area, your comfort performance starts to taper off. But if you have less than 5% free area, depending on the climate and depending on other building design factors, you're probably going to see ventilation performance and comfort performance start to drop off quite dramatically. So anecdotally, or I guess 5% is roughly the amount that codes and standards have decided most buildings in most climates where we're having natural ventilation would see an effectively good enough outcome for free area performance on a building. Now, how does this work today? So if you imagine, I'm just going to look at a house as a case study today, but if you imagine a large residential building with lots and lots of rooms, to do prescriptive compliance for free area is actually a real pain. Has anyone tried to do or show these calculations before? Yeah, there's a few people with their hands up. So this is a colleague's house that I helped design, and we didn't have a free area calculator when I helped him design it. And the study that I did on this project was very similar to the sorts of studies I used to do as a consultant doing naturally ventilated buildings. Grabbing 2D drawings and elevations, working out for each room how much window opening there was, comparing it to the floor area of the space, calculating the amount that was required, highlighting different spaces to communicate which ones were failing or not failing, and then trying to provide guidance as to how to improve the design. Now, this is a very tedious task. Has anyone done this particular task before? Yes. The front there, always put your hand up, great. Yes. It's a very tedious and time-consuming task and not very productive. So what we wanted to do was we said all of the information that we need to do this calculation is known by a 3D model. We should just do this calculation and provide this information for the user. Now, I don't know whether I can Alt-Tab out of this view, but I'm going to just try now and see if I can get this to work. Are you seeing my... no. Okay. I'm not quite sure how to... maybe if I leave presentation mode here and then go to this website. Are you seeing my website now? No? Sorry, this is definitely worth doing, so I'm going to try and do this. Is that happening now? That's up on the screen. Yes! Okay, cool. So, so this is Sefaira. I'm going to try and show you a few different scenarios happening with Sefaira today. If I can get this. This isn't my computer, unfortunately. No. Okay, fine. So this is the model that we imported into Sefaira, and essentially what we do now with free area is we provide a colour diagram to help someone establish which zones are passing and failing. So in this particular exercise that we had before, this was the difficult room. You can click on the room and it'll tell you exactly what the free area for the zones are for each particular room is, and whether or not it's passing or failing against your design criteria. And we also enable you to change either in the 3D modelling environment by tagging windows as fixed, or within the application you can change the openness factors and the proportion of glazing that's fixed, so that you can adjust it and optimise it to get to a state where we have more window openings. So for example, if I come in here, I'm going to throw caution to the wind and try and use an online software with some other. So for example, if I said, oh, the free area of my windows was much higher than I'm showing now, let's say it's 85%, hopefully what we'll see is this zone has passed and this zone is still failing. Now we have 3% free area, so we're probably going to have to go in and draw another window. So we wanted to make a really quick workflow for someone to draw or have a model drawn in SketchUp or Revit, upload it into Sefaira, and then very quickly generate a report, a spreadsheet that lists all the zones in their free area without you having to do anything. The thermal comfort is a lot harder to test. Let me just see here if I can go back to the slide presentation. Thermal comfort is ultimately what you're interested in. So just because we know what the free area is and there's some anecdotal evidence that 5% free area gets you to a good place, you're probably interested in talking to the architect about shading, thermal mass, window ratio, a whole lot of other things, and how these design features are going to affect the building performance. And essentially, if you go back to the free area curve, they sort of do this sort of thing where the free area curve might be constant, but if you put more shading on the building, you'll still get better comfort performance even at the same free area ratio. If you put more unshaded glazing on the building, it will go down. So there are a whole lot of different standards and benchmarks for thermal comfort. Hand up if you're familiar with different thermal comfort standards. Sorry, I'm going to be a real pain and make people put their hand up. Okay, cool, thanks. So, I've listed a few here. Dry bulb, operative temperature, predicted mean vote, TM52. There are many others. Today, just to keep it simple, we're going to give some examples using dry bulb temperature, but obviously all of these standards are things that can be used to test thermal comfort. Now, when you're designing naturally ventilated buildings, obviously there's a wide range of factors that you need to take into account: heat gain, radiation, convection, etc. And a lot of the time when we talked to people in the industry, we saw people were trying to do these sorts of studies. So I've got a whole lot of different options along the x-axis. How did my strategy affect the percent of time that the space would be comfortable? So I'm going to look at a project now. This is not a real case study. This is an imaginary building, but it sounds better if I say case study. So this is a Revit model that we put into Sefaira, and I'm calling it the Cambridge College Dorm Project because I live in Cambridge and I built the model there. So step number one, I might try and go into the app. Are you guys interested if I've got screen grabs, but are you interested if I faff around and try and show you in the app rather than just with the screen grabs? Is that worth me doing? Yeah, I'm getting a few nods, I'll do that. So let me just come in here, try and do that. All right. Revit keeps wanting to open, being in front of everybody else, which is pretty difficult. Is that there now? Okay. All right, so here I've got my my naturally ventilated dorm study. So in Sefaira, what I've done to begin with is I've already created a series of options. The reason why I've done this is because even though Sefaira does do fast simulations, when you come to a presentation that's 45 minutes long and you don't know how good the Wi-Fi is going to be, it's not the best idea to be planning to do simulations in front of everybody. So Simon might be able to tell me, is there a reason why you think that I couldn't open this, Simon? Aha, there we go. No. Okay, let's get a bit more space here. Good. All right. So I'm going to click the comfort, the free area section first. Let's say we've uploaded the model and we haven't really done anything with it other than just bringing it in. First step we do is do a free area study. You can now see all of the zones where the building passes or fails free area very quickly and see how much they pass or fail by clicking on them or downloading a spreadsheet. And then that gives us an opportunity to try and optimize the free area. So we'll do a quick optimization by changing the openness factors of the windows and getting better, if not completely passing free area results for our building. So first step would be get to a point where virtually all of the zones are passing or almost passing our free area requirement. So they're all green, light green, or just failing, which is the orange one. Now I'm interested in understanding the comfort. So in my space use requirements, I've said that this building, I want it to be between 20 and 25 degrees Celsius, which is down here. And so I'm interested in seeing how often I'd like to be between 20 and 25 Celsius for 98% of the time. And the first thing that it tells me now is it's done the dry bulb temperature calculation, and it's telling me that 47% of zones are failing. 47 zones are failing across 2 floors. The worst zone is about 7% under the target. So I can find out very easily by clicking on a zone what the percent of time it's comfortable, whether it's too hot, too cold, etc. So at the moment I'm not really providing comfort for my occupants. Well, if it's a naturally ventilated building and it's a dorm and it's in Cambridge and they're all sort of very bohemian anyway, we can probably relax the set points. So let's say that we're more interested in it having 26 degrees as an operative temperature target rather than 25. We can now see that some of the zones on the north facade are starting to get there in terms of being comfortable enough for us, for our building, right? So you can see these perimeter zones along the north facade are almost there. If I click on this number 6 here, 97.9% of the time it's within that set point range. But I still have a big problem on the south facade. So I'm going to try a few different things. I'll add night purge, a ventilation strategy which can be done during natural ventilation, deciding when the window's open. And I'll also add an external shade to the building. And now you can see that I'm getting to a point where the building performance is gradually improving and getting to a point where I'm passing the design, right? So, and then ultimately looking at an automated external shutter potentially is a better solution to doing this. And the results are telling me now there's only 2 zones failing. Perhaps I can look at those zones in a bit more detail now and work on optimizing those particular designs. But unlike a lot of early stage analysis where you have to make a decision about which zones are the worst zones before you do the analysis, this is giving you a full analysis picture of every single room in the building, and you can even download all of the dry bulb alley temperatures if you want from the output and get a really quick assessment of how the building is going. Now, what was I going to do? So you can see here, looking through the different stages of the design, relaxing the set point, adding night purge ventilation. Oh yeah, and then to communicate it all and roll up a story at the top, what I've done is I've chosen some thermal comfort metrics that let me communicate how the building is going. So the first column here shows the number of zones failing, and you can see as I go through the different strategy approaches, you can see how many zones in the building are failing under each of those strategies. So when we went and relaxed the set point, 10 of the zones suddenly passed. Once we added night purge, another 16 zone passed. And then once we put shading on the facade, we got almost the entire building to work. Similarly, you can see that expressed as a percentage. But what's also interesting is there are other quantifiable ways to assess this. This particular column looks at the average percent comfortable for all of the zones. And you can see that in that case, even in the worst case, even though 47 zones failed, or only 10% of the zones passed, it was still on average comfortable for 94% of the time. So not particularly horrible. And then you can also see what the comfort in the worst zone was. So that's a sort of study that you should be able to do within Sefaira in less than a day, maybe 4 hours. Is that half an hour? Yeah. Okay. Cool. Maybe in a few hours if you have a working model. Pretty quick study to do. So you can start to see how if I'm doing an early Reba stage 2 natural ventilation study, I can very quickly generate a story that I can tell to my client and tell them. Was I just looking at the thing without actually? Was I looking at the wrong thing? Okay, we're all good. Cool. So now let's say we've done all this work. 4 hours later, we have a really good natural ventilation strategy. We take it along to the meeting that afternoon because after all we did it the day before or the morning of. And then we get to the meeting and everyone says, that's great, but actually we don't want to spend that much money and we still want to have the same energy performance from that building. So can I quickly now do some energy reduction strategies or carbon reduction strategies within the software to make further improvements? For example, what happens if there's no natural ventilation? What happens if we take off the key features that made natural ventilation work? What if we tighten the set points again because there might be some, very well-to-do, well-heeled people that aren't so bohemian in this Cambridge college dorm that we're going to have? What if we wanted to do something that wasn't like chilled water fan coils, but maybe we just wanted a split system, etc., etc., etc. All these sorts of questions, very typical stage 2 questions. Just want to get a sense for what the read of different strategies is likely to be. So we've copied the project, gotten rid of all the old options. Now let's see if I can open this. I've created a new project in a new browser window. It's called Cambridge Dorm Carbon Study. I generated this just by copying my old project, deleting all of the old options, and I'm starting at the top now with my option 4B, which was the natural ventilation system with the automated external shades. And now I want to tell a story of how different changes are affecting not comfort this time, but the cooling and heating equipment and the annual CO2 emissions and annual energy cost of the building. And I can do this very easily, creating new options and then testing different strategies. So what I've done for you today is just showing how some of these different strategies played out. Now the first thing you might do is you might say, right, well, I know I'm going to turn off natural ventilation. I know that's going to do some add some extra fan energy and cooling energy. What's going on with my building right now so I can think about the most likely strategies that will improve the design. So very quickly I can get some nice inputs, some nice information about the energy breakdown for the building, seeing it on an annual basis, also on a monthly basis. And what you'll see that's quite interesting, and this is a result of the way that windows are controlled in natural ventilation systems with heating, is that there's heating occurring even during the summer months. Why is that? Well, when windows open and close, inevitably the heating system is going to be, is not necessarily going to be fighting the windows, but there'll be extra cooling happening in the building. There'll be cooler air happening early in the morning and late in the evening. And at the edges of the set point conditions, the heating will still need to operate a bit more than it would for a normal system. So let's look now and see what happens if we turn off the natural ventilation system. It actually reduces the cost of reduces the annual operating cost and the annual CO2 emissions. And if I look at the monthly chart now, you can see that winter energy has now been, the summer heating energy has now been replaced by a cooling energy load. So that's fine, but the thing is now I'm paying for an air conditioning system, I'm paying for external shades, I've got a very wide set point band, etc., etc. So to write the building up to something that's a bit more typical with more normal set point bands, I can make those changes and then quickly see how the energy performs in that particular option. And then add a few more scenarios, such as a split system, which is done really easily by changing the HVAC system in the drop-down menu here. Obviously, I go to a cheaper system, it's going to increase the operating cost and the carbon emissions. So perhaps as a SOP, now that I've removed the CO2, removed the expensive HVAC system, removed the exterior shades, and a few other things. I can go to maybe add 100 square metres of PV onto the building and then communicate the story. Now there's some really great ways in Sefaira that you can tell that story using this compare concepts graph. So a lot of the time we just want to see how the different options compare against each other on the basis of CO2, and here we can see how the different strategies have affected the total energy performance against each other by looking at the by comparing the different results. If I'm interested in seeing how the energy mix affects that, I can also look at energy mix, which will take into account the renewable energy of the building, and there you can see that when I think about that 100 square metres of PV and how that's affected the project, it's actually going to make that last option stand out in terms of overall carbon emission performance. Sefaira provides really nice graphs then that can just be exported from the software and put straight into a slide deck. So these are some graphs that were just exported so I can start to tell my story. Yes, we started out with this is our CO2 pie chart. We had a lot of heating. This is the heating was occurring in summer, so we moved to go back to air conditioning, but of course we had to improve the performance of the building, and that meant that the energy went up, so we added some renewable energy, and there we are. That's the very, very short cliff notes of the design story for reducing the carbon emissions on this fictional project. Of course, now to check, what the cost is likely to be, the contractor would like to know what the preliminary HVAC sizing is going to be. So fortunately, Sefaira has done separate HVAC sizing calculations as well, and we can very quickly download those. You can grab the Revit Energy Plus sizing and loads report, which provides a sort of very engineering type report. And let's see if this works live. Provides you classic sort of engineering report with the load summary and the component summary for each of the zones within the building. This is straight out of Energy Plus. And we also provide and we also provide a spreadsheet that lets you, and it's probably blocking it now because I picked the wrong option, that gives you a tighter summary of the equipment loads of all of the different components that are going into the building. So that each of the zones you can get the fan coil size, the cooling load, the heating load, the time of day, etc. that the loads occur on the equipment. Finally, I just thought I'd share as well that not only can you use the model to do all these studies, but perhaps if you want to provide a little bit more information for your client, you can do a daylight study that's like this, that looks like you spent, at least 3 or 4 days on the analysis, but actually you just clicked run in Sefaira and got a good visualization of what was going on. So we'll go into this model here. And I'm just going to change some context here and add the different components of the building onto the facade. So this is one of the models I showed you at the beginning, and it was a model that was used for our ASHRAE Lowdown Showdown competition at the ASHRAE Energy Modelling Conference last year. What's really cool about this project was this project was done, there's the SketchUp model that was used for the project, and within a few moments we can do any sort of simulation, and hopefully this is going to work. What was really cool about this competition was there was a bunch of architects and students who'd never used the software before, got together for the ASHRAE Lowdown Showdown conference, had to build a medical office building of a certain size and do some energy performance analysis on that building. They were all able to learn the software, get a working model in, do the competition, and provide sensible results in front of an audience of energy modelers. And I was really proud of the fact that they were able to do that, because our whole goal of our software is to empower people who either want to do things very quickly or who find traditional software just with perhaps too much of a steep learning curve to get started, being able to use Sefaira. And now it's probably going to have something going on here, but anyway, we'll see. Oh, there we go, it's about to come back. So I did want to make sure I had a few moments for questions. I'm not quite sure how long we have, but 5 minutes. Okay, cool. So in summary, why think about Sefaira? Don't see Sefaira as a replacement for all of the great software that you already use that you're going to hear about today. Okay, it's not a software tool that's meant to do compliance. Hopefully no one got that impression today. What Sefaira is focused on early stage tasks. Make it really, really easy for you in 4 or 5 hours to get some really cool material together to present to a client when you don't have time and you don't want to make up the results. It's fast and easy to use, it's accurate and reliable, and hopefully that's piqued your interest. And if you want to talk to anyone about it, I'm here, and Simon is wandering around as well today. So yeah, look forward to hearing from you. Thanks. I think we've got maybe 3 or 4 minutes for questions now as well, if anyone has a question. Thank you. Does anyone have a question? Oh yes, yep.
Your percentage floor areas for the natural ventilation design is still a little bit rule of thumb-ish, and I just wondered, when you test the efficacy, what part of the energy plus engine are you using? Are you using the airflow network? Because, for example, a 1 square metre window is a fixed percentage of the floor area, but if I were to split that 1 square metre into 2 half-square metre windows and separate them by a height difference, I'm going to be increasing the airflow through the same 1 square metre. So I just wondered, when you're testing the efficacy, how is Sefaira calculating whether or not you're meeting the comfort levels?
Okay, great question. So I think that the question, in summary, is a bit of a question about how is Sefaira doing the efficacy of the natural ventilation calculations in Energy Plus, sort of summarised. Yeah. So we are using the FI network calculations, and it takes a little bit longer because of that. So that's one of the reasons why I didn't want to show it today. What we are limited at the moment in our interface to do not to have interzone airflow. Okay, so the zones are all single zone studies. So you can see on the study that I presented, it's looking at apartment buildings, school rooms with single-sided ventilation or multi-sided ventilation, but it's a single zone analysis. Okay, we will ultimately get to a point where we can do cross-flow ventilation. So it does use the airflow network calculation. But if you know, like essentially any bulk airflow modelling type approach, if you put lots of windows in there, it's only going to sort of do so much if it's all in the same zone, right? So you shouldn't expect like having windows in lots of different places to make a huge difference to the results if you're doing a bulk airflow study and it's all in the same zone. Does that answer your question?
It does, yes. Yeah.
Cool.
Okay, we have. Sorry.
Another point was you not mentioned the coefficient of discharge. So is that fixed within Energy Plus, or can you alter that? Because obviously some windows are going to have different airflow properties.
You can alter it in the user interface.
Excellent. All right, thank you.
Okay, we have time for one quick question.
Yes.
I was curious about the way you do the zoning. So in SketchUp, there's actually no object that is to base that on. So what is the process for finding the zones in SketchUp?
Yes, so the question, thank you for the question. The question was how do we do the zoning in SketchUp? And essentially we draw lines on the floor plate. If you just simply draw lines on the floor plate to denote where the zones are, and then we use that to define the zone boundaries. Right. So yeah, it's pretty straightforward.
Okay. Thank you very much. I think that we are out of time.
That's great.
Thanks very much. So can we thank our speaker? The next person to speak is Paul Demi. Thank you.